Have you ever looked up at the night sky and wondered where it all came from? How did this vast, incredible universe begin? Well, let's travel back in time, way back, to the very beginning. Imagine everything, and I mean everything, all the stars, galaxies, planets, you, me, this very screen, all squished into a single point. A point smaller than a single atom, incredibly hot, and unimaginably dense. This wasn't a big empty space with a tiny dot in it. This point was the entire universe. There was no outside. Then, about 13.8 billion years ago, it happened. The Big Bang. This wasn't an explosion in space, like a firecracker. It was an explosion of space itself. In a fraction of a second, the universe expanded faster than the speed of light, a period scientists call inflation. From a subatomic size, it ballooned to something much, much bigger. As the universe expanded, it also cooled down. In the first few seconds, it was a searing hot soup of fundamental particles, quarks, electrons, photons. Think of it as a cosmic particle accelerator. It was so hot that atoms couldn't even form. If you tried to stick a proton and a neutron together, a high-energy photon would just blast them apart. After a few minutes, things had cooled enough for the first atomic nuclei to form. Mostly hydrogen and helium, the lightest elements. But we still didn't have atoms as we know them, because the universe was still too hot for electrons to be captured by these nuclei. It was a dense, foggy plasma. Light couldn't travel far. Photons were just constantly scattering off free electrons. The universe was opaque. Fast forward about 380,000 years. The universe had cooled to about the temperature of the surface of a star. Finally, it was cool enough for electrons to combine with nuclei and form the first stable, neutral atoms. This event is called recombination. Suddenly, photons were free to travel through space unimpeded. The universe became transparent for the first time. The light from this moment is still traveling across the cosmos, and we can detect it today. It's called the cosmic microwave background radiation, and it's like a baby picture of the universe, a faint glow in all directions. It's one of the strongest pieces of evidence we have for the Big Bang. But the universe was still pretty uniform. There were no stars, no galaxies, just vast clouds of hydrogen and helium gas. However, there were tiny, minuscule variations in density. Some areas were just a tiny bit denser than others. And gravity, the quiet, patient force, went to work. Over millions of years, gravity pulled more and more matter into these slightly denser regions. The clouds of gas grew larger and more massive. As they collapsed under their own weight, the pressure and temperature at their centers skyrocketed. Eventually, it became hot enough to ignite nuclear fusion. The first stars were born, lighting up the cosmos and ending the cosmic dark ages. These first stars were giants, hundreds of times more massive than our Sun. They burned through their fuel quickly and died in spectacular supernova explosions. These explosions were crucial. They forged heavier elements, carbon, oxygen, iron, all the stuff needed for life, and scattered them across space. These enriched clouds of gas and dust then collapsed to form new generations of stars and planetary systems. Gravity also pulled these stars together into massive structures. The first galaxies began to take shape. These galaxies then clumped together to form clusters and superclusters, creating the vast cosmic web we see today, with huge voids of nearly empty space in between. And all this time, the universe has continued to expand. But here's a twist. We used to think gravity would eventually slow this expansion down. But observations in the late 1990s showed something shocking. The expansion is actually accelerating. Something is pushing space apart. Scientists call this mysterious force dark energy. We don't know what it is, but it seems to make up about 70% of the universe. The rest is mostly dark matter, another mystery substance that provides the extra gravity to hold galaxies together, with normal matter like us making up only about 5%. So, from a hot, dense point to a vast, accelerating cosmos filled with galaxies, stars, and mysteries like dark energy and dark matter, that's the story of the Big Bang. It is a story written in the light of distant galaxies and the faint glow of the universe's first light. It's our story. And the best part? We are still figuring it all out. Thanks for joining this journey through time. If you enjoyed this cosmic tale, don't forget to like, subscribe, and hit that notification bell for more explorations into the wonders of our universe. See you next time. From that initial state, it has been expanding and cooling ever since, creating everything we see today. This idea wasn't just pulled out of thin air. It started taking shape in the early 20th century. Scientists like Alexander Friedmann and Georges Lemaitre used Einstein's new theory of general relativity to propose that the universe wasn't static, it was actually growing. Lemaitre, a Belgian priest and astronomer, was the first to suggest that if the universe is expanding now, it must have been smaller in the past, originating from what he called a prime-val atom. But a great idea needs great evidence. The first major clue came from an astronomer named Edwin Hubble. In the 1920s, Hubble was observing distant galaxies, and he noticed something strange. The light from these galaxies was stretched out, shifted towards the red end of the spectrum. This smoothed out the universe and set the stage for the structures we see today. As the universe continued to expand and cool, the fundamental forces separated. Quarks and other elementary particles formed a hot soup. By the time the universe was about 1 second old, these quarks combined to form the first protons and neutrons. For the next few minutes, a process called Big Bang nucleosynthesis occurred. But the universe wasn't perfectly uniform. The CMB shows tiny temperature fluctuations, minuscule variations in density from one place to another. These tiny seeds of structure were crucial. Over millions and billions of years, gravity went to work. The slightly denser regions pulled in more and more matter, growing larger and larger. These clumps of matter eventually collapsed under their own gravity to form the first stars and galaxies. The first stars were massive, bright, and short-lived. When we look at how galaxies rotate and how galaxies cluster together, we see that there's not enough visible matter, stars, gas, and dust to account for the gravitational pull we observe. It's as if there's an invisible mass holding everything together. We call this mysterious substance dark matter. It doesn't emit or reflect any light, so we can't see it directly, but we know it's there because of its gravitational effects. Scientists estimate that dark matter makes up about 27% of the universe.